Welcome to episode 4 of the Don Paul podcast. Today's episode: what makes the forecasting of lake effect snow so damn hard? Pardon my language, but I do want to get into some of the variables we don't often have time to explain in detail on the air. And so then you can learn that we are dealing with something even more complicated than you already suspected. There are some key ingredients that are musts to making lake effect snow. The first one is something called the lapse rate, the temperature drop off rate from the relatively warm lake surface to the atmosphere about 5,000 feet up. We know that we need a drop off rate of about 13 degrees Celsius in those first 5,000 feet to typically get some well organized lake effect snow going. That lapse rate induces upward motion from the warm, moist air near the lake surface, with condensation in the Arctic air aloft, and the snowflakes begin to get dumped out. Now, the lapse rate can become greater than 13 degrees Celsius, and once we're confident looking upstream that lapse rates are going to be getting into 20, 21, 22, 23 degrees Celsius, then we are confident the instability in that lapse rate will range to extreme, which will produce some violent updrafts. And it is a convective process. And that's when you not only get the super heavy rates of snowfall, but you also begin to see lightning and get the sound, thunder, snow. And that's kind of the setup we had during the deadly Christmas blizzard last year. We had an extraordinary lapse rate. And then another element that gets less mention is adequate humidity in the air mass overall. Now, if we look up wind and see very dry air over Michigan, northern Ohio, and Wisconsin, air starting out so dry, moving over Lake Erie, will pick up Lake Erie moisture, but it will produce less precipitation than it would have if it had originated from a moist air mass. So that's another ingredient. Another element, especially for the Buffalo metro area, is the fetch of the wind direction. How much of the lake's waters will be traversed by these cold winds, and the key wind direction on a compass. You picture 360 degrees, let's divide it up into 5-degree increments. The wind vector that produces the longest fetch is 250 degrees on the compass, and that would, in a lake effect situation, deliver the heaviest lake snow right into downtown Buffalo, Cheektowaga, the airport, out toward Batavia, maybe even farther to the northeast when it's really well educated. And then we want to look at the uniformity of the wind direction with increased altitude. If it's 250 at the surface, but you go up to 10,000 feet and it's 280 or 290 at that elevation, that's a kind of directional wind shear which will tear away at any organized lake effect band. You may still get some, but it's going to be poorly organized and just kind of sprayed scattershot. Where wind shear in 10,000 feet of under 30 degrees tends to allow much better organization for the lake effect band. The band often takes on a very straight appearance, but there are subtle curvatures to the wind flow which can affect how much lake effect snow you're going to get and where it's going to go. Now, any low pressure system in meteorology is called a cyclone, and the counterclockwise circulation in the northern hemisphere around a low pressure cyclone is cyclonic. Cyclonic curvature, which then increases the lift, and that increases the amount of cloud cover and precipitation. Where the opposite is if the flow is moving across the top of a high pressure ridge. A high pressure ridge is an anticyclone, and anticyclonic curvature tends to dry and produce some sinking air. So if we're confident in output from the models that we're going to progress from a cyclonic curvature to an anticyclonic curvature over a couple of days, we can forecast with some confidence that the lake effect snow will weaken and maybe even dissipate. So then we deal with the issue, the word you've heard so often, oscillating lake effect snow. Oscillations are typically caused by approaching disturbances in the mid-levels of the atmosphere, linear troughs of low pressure. Now, out ahead of a trough, the winds typically back from westerly to more southerly, and that can send a band northward. If the backing is subtle, But if the backing is extreme, that can just tear apart a band for at least several hours. And once the trough goes to the east of us, the winds veer behind the disturbance. That means they go from south back to west. So if a trough is approaching, a band may move from the western southern tier into northern Erie County in fairly short order, depending on the nature of the trough. And then once the trough goes by, it can go from, say, Lockport quickly back into the hilly terrain to the south. So oscillations are now forecast with more reliability because we not only can look at upwind observations at the surface and aloft with data gathered from weather balloons, but we also have computer modeling that's much higher resolution than it was when I got here in 1984. And another key ingredient is the wind direction and the precision of the boundary layer, these lower level wind directions, is absolutely critical. If you're off by 5 degrees in the wind direction forecast, you can warn or not warn the wrong 100,000 plus people, especially in the northern half of Erie County, the most densely populated part of Western New York, that starts at West Seneca and Lackawanna and goes through Buffalo, Cheektowaga, Kenmore, Amherst, Clarence, Akron. And so if you were expecting 250 degrees and the wind ended up coming in more from 255 degrees, that would tend to focus more on South Buffalo and much less so on downtown and North Buffalo. And in the Snowember event of 2014, for example, we had winds which often focused on a 255-degree vector, producing 48 inches or so in South Buffalo, while in North Buffalo, where Channel 4 is, we had about 4 inches. And if you're wrong 5 degrees in the other direction, you can imagine the impacts. 245 tends to miss most of Buffalo, but gets at least the southern portion of Amherst, northern Cheektowaga. 240 more the northern half of Amherst, Clarence, Akron. I'm oversimplifying this a little bit, but this kind of precision in wind direction forecasting was essentially inconceivable when I first got here. We didn't have the computer crunch power to make high resolution models. And now, while far from foolproof, we are doing better. But getting back to that issue of cyclonic curvature, one part of it, which appears to have occurred on November 27th, is the cyclonic curvature produced by the still very warm lake surface on Lake Erie. Warm, moist air up just above the lake has lower density, lower barometric pressure, and that increases the already cyclonic curvature even more so. And models don't pick up on that so well. That's more a matter of pattern recognition on our part. And the meteorologists, we have to keep that in mind. And that is probably what sent what Lake Snow was originally expected to focus more on more rural southern Erie County into East Aurora, Orchard Park, and the more densely populated Buffalo South towns. That lake-induced cyclonic curvature tends to dampen down as the lake gets colder. And once lake temperatures get closer to the mid-30s, there'll be less of that. Then sometimes, to finish up here, uh, it may still be bitter cold, bitter cold at the surface in a lake effect snowstorm, but you notice the lake snow is starting to peter out, even though the surface temperature hasn't changed. That can be tied to warmer air moving in aloft, which you won't feel when you're standing outside in your driveway, but that lessens the lapse rate. And I'll finish up with the least mentioned lake, even though it deserves more mention. Once the veering takes winds around to 280, 290 degrees, big fat Lake Huron starts to come into play. And in a 290-degree wind orientation, you can get multiple skinny bands with moisture from Georgian Bay and Lake Huron, as well as Lake Ontario coming more into play, especially in eastern Niagara, Orleans, and northern Genesee counties. That's when you get those more multiple skinny bands, generally with a more northwest flow. The amounts of snow in western New York tend to slacken off quite a bit and become more scattershot. So those are the basics. I've tried not to dumb this down too much, but I hope you've enjoyed it. And if you have, Please spread the word, not just about this episode 4, but also my podcast in general. And if you don't like it or didn't like this episode, please keep it to yourself. Give a guy a break. I shall be chatting with you again in the very near future.